устойчивости, появления устойчивых организмов к антибиотикам. Профессор Олтмен закончил Исследовательский технологический институт в 1960 году. Он получил степень бакалавра наук. Затем в 1967 году в университете лауреата он защитил кандидатскую диссертацию. Дальше у него было две стажировки постдокторские в Харвардском университете в 1967 по 1969 год и в Кембриджском университете в 1969-1971 году. В 1989 году он был удостоен Нобелевской премии по химии вместе со своим коллегой Робертом Чехом. Профессор Олтмен является почетным членом Национальной академии наук Соединенных Штатов Америки и имеет несколько почетных степеней различных университетов. Профессор Олтмен, I'm giving you the podium for to your lecture, and we are looking forward to your lecture.
Большое спасибо. Я говорю немножко по-русски, а сегодня я говорю только по-английски. Let us start. If you look at DNA in a book, you see some straight lines or some wavy lines in 2 dimensions. However, DNA is a molecule like any other chemical molecules, and it obeys all the rules of chemistry. The same is true of RNA, which is transcribed from DNA. One of the seemingly endless rules of chemistry is that a large molecule like DNA or RNA can suffer mutations or changes. For example, the people who won the Nobel Prize this year for chemistry studied repair mechanisms of DNA. That is to say, you can alter the composition of DNA, and other enzymes inside cells will come by and repair the damage. So I'm going to talk about a certain class of mutations to begin with, but ultimately I'm going to talk about the worldwide problem of drug resistance. That is to say, resistance of bacteria, or for example, the parasites that cause malaria, to various drugs, and what we can do about them. Now, if you let DNA sit in the sun, for example, on your skin, for example, certain parts of it will change. That is, there are 4 nucleotides which make up the total sequence of DNA. A, T, G, or C are the abbreviations in English. And you can, for example, change a T into a C. So in a 2-dimensional and double-stranded structure of DNA, normally T always pairs with A. That is, I'm talking about Watson-Crick hydrogen-bonded pairing. T pairs with A and C pairs with G. If you have a mutation of the kind I'm describing, that is a T changes to a C, then you might have a pair that looks like AC, and that's not good for DNA. So if you have a gene, that is a section of DNA, that is responsible for coding for drug resistance of a bacterium, excuse me, one change can alter something that was sensitive to a particular drug to become resistant to a particular drug. Okay? Now, If you have any trouble understanding what I am saying, please put up your hand and ask a question. I have no problem with people asking questions during my lecture. So let's say we have DNA and it undergoes a mutation, and the properties of the gene that contains that DNA changes. And I'm talking about genes that code for resistance to various drugs. So, for example, there are genes that code for resistance to penicillin or ampicillin, which is a derivative of penicillin, or various other drugs of that kind. Now, let us talk for a moment about the problem of drug resistance. It is, as I said, a worldwide problem. And you can consult any reputable journal that keeps track of statistics of drug resistance, and you will see the problem immediately. And I'll get to that in a minute. But right now, let's talk about populations of bacteria, for example. If you have a population of bacteria, and you can denote it by a certain number, a very small number of that population will become automatically drug resistant through spontaneous mutation, in which the recurrent mechanism does not operate properly. If you increase the total number of that population, let's say going from 10 to the 8th in 1 mil, that's 100 times a million bacteria in 1 milliliter, to 10 to the 9th, then the number of mutations that code for bacteria that are resistant to any particular drug will also go up by tenfold in that particular population. So one has to keep that in mind. Now, the problem of drug resistance has several points of origin. One of them is that there is overprescribing of drugs by physicians. That is to say, there are many physicians, if you go to them and say you're complaining of something, they will automatically prescribe the drug. Okay? In many cases, that's not correct. And that's true all over the world also. If you have a common cold, and you go to a physician, and you say you're not feeling well, and he prescribes a drug, leave that office immediately. Don't even check to find out the physician's name. That physician is making a mistake. There are no drugs for the common cold. Colds are caused by viruses, and we don't know yet of any drug that will cure viruses that cause common colds. So that is one problem, overprescribing of drugs by physicians. So they are increasing the total number of bacteria in the world, so to speak, and therefore the number of bacteria who are resistant to specific drugs. Now, the second problem is overuse of bacteria and drugs in animal feeds. If you are raising cows or pigs or chickens and you put drugs into their food, those drugs ultimately, the bacteria that are resistant to those drugs, and there must be some in the population that are being fed to the various animals, those bacteria will survive the application of those drugs and ultimately will find their way into the human food chain. So that's another way of increasing the number of bacteria that are resistant to various drugs. In various parts of the world, and I will use the phrase third world countries, you can buy prescriptions over the counter. That is to say, you don't have to go to a physician to get various antibiotics. You just go somewhere where you know they are selling drugs and you can get whatever you would like. That is another way of increasing the number of drug-resistant bacteria in the general population. So in every one of these cases that I'm mentioning, you're either increasing the number of bacteria, and therefore the number of bacteria that are resistant to drugs, or directly increasing the number of bacteria that are resistant to various drugs. Another problem, which is a little harder to quantitate, is that the selling of antibiotics or drugs is very profitable to major industrial companies that produce drugs. It's not very expensive for a large pharmaceutical company to produce these drugs, and they do so, and they sell them all over the world, particularly in the third world, and they make a significant profit off it. Okay, so there are four sources of the problem that I've mentioned today. And of course, aside from these mistakes of the human population, there's the natural mistake that mutations are causing more bacteria to become drug resistant. Or to find a new antibiotic that will work where current antibiotics don't work appropriately. Now, there have been various reports over the last few years, mainly the WHO, the World Health Organization, puts out reports every few years with statistics about the number of people around the world and their countries in which drug resistance is a problem. What I'm going to talk about right now is an article by Chinese authors published in 2013, a very good, sensible article on drug resistance in various countries. In this article, it is stated that every year in China, 80,000 people die because they are resistant to various drugs. Okay, so these people have a disease, they're treated with various drugs, but the drugs have no effect because the bacteria themselves are resistant to the effects of the drugs. And that's why 80,000 people, a fairly large number, can die every year in China. The figure for Western Europe is 25,000 per year, and for the United States, this is for a few years ago, is 23,000 per year. These are enormous numbers of people who die because we don't have the right tools to treat them. And the right tools are drugs that are very active today against bacteria that are drug resistant. I have a little bit of data for Russia. I managed to find something that was published, let's say 15 years ago or so, on a number of people in hospitals in Russia who had tuberculosis, TB, but who were resistant to the drugs used for treating tuberculosis. And for example, in Moscow, for the hospitals that are mentioned, the number of people who are resistant to the usual drugs for treating tuberculosis ranges between 25% and 75%. So that's, let's say, at least 15 years ago. And the number of people with TB in Moscow hospitals who are resistant to drugs is just enormous. It's almost as if you've got TB, you might as well not bother going to a doctor because the chances of you being cured are very small because of drug resistance. When I say drug resistance, I'm really talking about bacteria. They are resistant. Of course, if they're inhabited in people, then you can say people are drug resistant too in that regard. And the same thing is true of the malaria parasite. Now, just to go over a few drugs that are in current use, I'll go over them quickly. Most of the drugs in use today have what is called a molecular weight of about 500. For those of you who are not in tune to the science, all I will say is you can add up the number of carbon, oxygen, hydrogen atoms, sulfur, nitrogen, if there are parts of these drugs, and the total number of atomic weight will come to about 500. And that's more or less true of many different drugs. Ultimately, the drugs that I'm going to talk about today have a molecular weight of around 9,000, which is considerably larger. But we'll get to that in a few minutes. Now, for gram-positive bacteria, and I should say there's a way of distinguishing between bacteria as to whether or not they stain with different dyes. You can have a glass plate with bacteria on it, you can have a dye, and the dye will either turn a certain color or will not turn a certain color, and the gram dye is one of them. So for bacteria, I'm going to talk about the one called Staphylococcus aureus. This is a very common bacteria. It occurs frequently in hospitals. So many people in hospitals who are drug resistant are resistant to the effects of Staphylococcus aureus by different drugs. And there's one particular strain of Staphylococcus aureus, and it's abbreviated as MRSA, M-R-S-A, and it occurs frequently in drug-resistant patients in hospitals. The drugs that are used frequently to treat the MRSA strain are, for example, methicillin, related to penicillin, and vancomycin, which is a new drug, a relatively new drug, very powerful, and it's used in cases which seem hopeless. In the USA, about 5 years ago or so, 100,000 people per year become ill with Staphylococcus aureus infections. Now, the number has obviously grown since then, but the number of people at that time who died every year, excuse me, because of Staph aureus infections was about 25,000 or so. For mycoplasma tuberculosis, the number of drugs used are isoniazid and rifampicin. If you don't recognize these names, don't worry about it, it's not important. The number of people worldwide about 10 years ago who were infected with drugs that cause TB was about 10 million per year. Incredible. And perhaps something like 1 million of those people die every year because of drug resistance. The number of people who are resistant to drugs that affect Plasmodium falciparum, again, the name is not important. This is a parasite that causes malaria. About 2 million people per year are infected with this parasite, and about 750,000 people die every year because they're resistant to drugs that are used to treat Plasmodium falciparum. Most of those people who die are women and children. And the number of drugs that are used against them are chloroquine and pyrimethamine, two older drugs that are not so effective anymore, and artemisinin derivatives. That's a newer drug, and one of the people who won the Nobel Prize for Medicine this year, Yu Tu, is a Chinese woman who, on hints of what may have been true a couple of thousand years ago in Chinese folklore medicine, managed to isolate the first artemisinin derivative from plants in China. And now, of course, it's made on an industrial scale, and it's quite useful. We can go on from there and talk a little bit about the mechanism of a new kind of drug that my lab is working on, and a few other labs around the world are also working on something similar. So this does involve a certain amount of science, and I beg your indulgence to listen to this.